Welcome to the video summary series for Padisco's Introductory Statistics textbook. In addition to chapter summary videos such as this one, Introductory Statistics also offers podcasts, virtual tutor e-learning, homework activities with anti-cheat and auto-grade functionality, and detailed instructor resources. Find out more at padisco.com/introstats. For now, over to the author.
Hi again, I'm Sean Thompson and welcome to the next summary in the Padisco Introductory Statistics series. In this one, we're going over measuring data. In particular, we'll be covering measures of centre, measures of variation, and measures of relationship. So far we've looked at data and how it can be presented. When you've collected a bunch of raw data, like this one for example, the raw data probably won't help you much. But you can present the data, providing a visual summary of it. For example, that raw data could be summarised in this histogram. And now that's much better. We now have a better feeling for the data, but feelings can be subjective. And pictures of data, as presentable as they are not susceptible to rigorous statistical analysis. What we'll find is that we need to measure data. Measurements of data are less subjective and can be mathematically manipulated in rigorous ways. Measuring the centre of data is all about numerically summarising where data values are. So a measure of centre is typically a number, and that number gives us some sort of indication of where the data values lie. A very common measure of centre is the mean. The mean of a set of numerical data is just the statistical average of all the numbers in that data. So say for example we have a sample of 5 test scores. Then to calculate the mean, we add the 5 values together and divide by 5, the number of data values. So in this case the mean is 11. At this point it's worth noting that the mean takes into account all 5 data values. If you change any one data value in that set, you will definitely affect the mean. So the mean could be said to be a measure of centre that is sensitive to changes in the data. Another common measure is the median. This is the data value that is ranked in the middle when the data values are placed in numerical order. So that data set we just saw, we can rearrange it so that the values are in order, like this. And the middle value is the third value, 12, and so this is the median. The final measure of centre we have is the mode, and this is the most commonly occurring data value in the set. So in the data set of 5 values, the value 12 occurred twice, which is more than any other value, so the mode in this case is 12. So that's the 3 main measures of centre: the mean, the median, and the mode. The mean and the median are the most commonly used measures. And these 2 measures will, of course, provide different summaries of your data, as we just saw in the example we were just looking at. And sometimes they'll be very different. And this is most pronounced with skewed data. For example, for the data in this histogram, the mean will be less than the median. And this is because, as we mentioned earlier, the mean is sensitive to all the data. And in this case, it's sensitive to the very low values, which drag the mean down. So when you use measures of centre, the measure you choose to use can have an impact on the sort of summary you're going to provide for that data. Whereas measures of centre tell you about where the data values are, measures of variation tell you about how spread out they are. This is particularly important because values that are spread out are less consistent than values that are not spread out. That is, values will vary more from sample to sample. And this is important because it means we can't be as confident in the data if there's more variation. So variation will tell you something about how much you can use your data to infer things. The crudest measure of variation is the range. The range is simply the difference between the maximum and minimum value in the data set. For example, let's say we now have a sample of 7 test scores. Then the maximum value is 99 and the minimum value here is 41. So the range is the difference between these 2 values, which is 58. The maximum and minimum values are 2 important values when measuring variation. 3 other important values are the 3 quartiles in the data. The 3 quartiles divide the data up into 4 quarters, hence the name quartile. The second quartile is the value ranked in the middle. That is, it's the median. It divides the data set into halves. The first quartile is then the middle value in the bottom half, and the third quartile is the middle value in the top half. For the 7 test scores we just saw, the quartiles split the data up like this. The 3 quartiles, together with the minimum and maximum, form what is called the 5-number summary. The 5-number summary can be represented graphically with a thing called a box plot. Now this talk is just a summary, so I won't go into detail here on exactly how the box plot is constructed. If you want to read more about how to construct or interpret a box plot, you can read all about them in the PDISCO Introductory Statistics textbook. The difference between the third quartile and the first quartile is known as the interquartile range. So for the 7 test scores, this interquartile range is the difference between 87 and 52, which is 35 in this case. So now we've looked at ranges and interquartile ranges and box plots. They all provide a fairly rudimentary measure of variation in data, but the most common measures of variation are the variance and standard deviation. Now these measures are more complicated. Like the mean, they're formulas that take into account all the values in a data set. The standard deviation is actually just the square root of the variance. So for now we'll spend our time focusing on the formula for the variance and where that formula comes from. The idea is that the variance measures the average distance from each point to the middle of the data set. And here we use the mean as our measure of the middle. However, it turns out that the best way to measure this average distance is to actually square the difference between each data value and the mean. So the variance is calculated by squaring the difference between each value and the mean, adding these squared differences up, and then dividing the sum by n-1. So you divide by 1 less than the number of data values. We won't here go into exactly why you divide by n-1 instead of by n to get the average distance, but rest assured that the formula does work better that way. As I mentioned earlier, the standard deviation is the square root of the variance. And really, in terms of measures of variation, the standard deviation is the single most commonly used measure. We've looked at measuring the centre and variation in a set of data for one variable. Now let's turn our attention to data for 2 variables and measuring the relationship between such variables. Recall that the way we present the relationship between 2 numerical variables is through a scatterplot. But, like with data for one variable, such a presentation can be subjective and not particularly rigorous. What we'll do here is show a way of measuring the strength of any linear relationship between 2 numerical variables and also measuring the nature of that relationship. The strength of linear relationship between 2 variables is measured by a thing called correlation. Here is the formula for the correlation between 2 sets of data. It looks fairly complicated, and it is. But the important thing is not to be able to calculate a correlation. We usually get software to do that for us. The important thing is to be able to interpret what the correlation means. Now the important things to note for correlation are, the correlation will always be somewhere between -1 and 1. If it's positive, that means that there is a positive association between the 2 variables. The scatterplot slopes up to the right. A negative correlation means a negative association. The scatterplot slopes down to the right. And the closer the correlation is to either of the 2 extremes, that is, the closer it is to -1 or 1, the stronger the linear relationship is, and a correlation close to 0 suggests a weak linear relationship. Now, to get a feeling for the significance of the correlation as a measure of linear relationship, let's try a question from the PDISCO workbook. In this question, there is an investigation into any relationship between the salary paid to a CEO and the productivity of that CEO. A scatterplot of collected data is given, and based on this, you're being asked to nominate a suitable value for the correlation. Of the options given, the only possible correlation here is 0.67, so we'll submit that. And now we get personalised feedback and an explanation for the question. So that's measuring the strength of linear relationship between 2 variables. As for the nature of such a relationship, we can always derive a linear equation called the line of best fit. That's a line that takes into account all the points on a scatterplot and comes up with a line that best fits them, hence the name. You can actually work out what the line is, and the formula for the line of best fit is here. The important thing to note is that, like any straight line, the equation for the line of best fit has 2 coefficients, and the coefficients for this line are determined by all of your scatterplot data. To get an idea of how well the line of best fit does describe the relationship, here are some examples of some scatterplots and the lines for them. So that was measuring data. The key topics were measures of centre, measures of variation, and measures of relationship.